Somewhere out there, right now, a planet stares at its star. It never blinks. It never turns away. One half burns under eternal daylight, while the other half freezes in endless night. And right there, at the boundary between fire and ice, something extraordinary might be happening. This is not science fiction. This is the reality of worlds we have already discovered, orbiting distant stars in our galaxy. They're called eyeball planets, and they challenge everything we thought we knew about what a habitable world should look like. When we think about planets that could support life, we usually picture something like Earth, a world that spins on its axis, giving every part of its surface regular doses of sunlight and darkness. A world with seasons, with weather patterns that distribute heat around the globe, with liquid water across much of its surface. But the universe, it turns out, has a much stranger imagination than we do. Most of the potentially habitable planets we have found so far orbit red dwarf stars. These are small, cool stars, far dimmer than our sun. To receive enough warmth for liquid water to exist, a planet must huddle close to such a star, sometimes closer than Mercury orbits our sun. And when a planet orbits that close to its star, something inevitable happens. The gravitational pull of the star locks the planet in place, forcing it to keep one face pointed starward at all times, just as our moon always shows the same face to Earth. The result is a world divided. The side facing the star receives constant illumination. The side facing away never sees a sunrise. There is no dawn on these worlds. There is no dusk. There are only two eternal kingdoms, light and shadow, separated by a ring of perpetual twilight. Now, picture what happens on such a world if it has water. On the day side, the relentless stellar radiation heats the surface. Water evaporates, rises into the atmosphere, and drifts toward the night side, where temperatures plummet far below freezing. There, the water vapor condenses and falls as snow, building up vast glaciers that grow ever thicker over millions of years. The night side becomes a frozen wasteland, a hemisphere of ice kilometers deep. But the day side tells a different story. If the planet is at just the right distance from its star, the substellar point, that spot directly beneath the star where the light is most intense, could host a circular ocean. Liquid water pooling in the warmest region, surrounded on all sides by ice. From space, this would look remarkably like an eye, a dark pupil of ocean staring up at its star, ringed by the white of frozen wilderness. This is the cold eyeball planet. The geometry is striking. The ocean might be hundreds or even thousands of kilometers across, depending on the planet's distance from its star and the composition of its atmosphere. At its center, the water would be warmest, perhaps even hot. Toward the edges, where the ice begins, temperatures would hover near freezing. This creates a gradient, a spectrum of thermal environments within a single body of water. And where there are gradients, there is potential for complexity. Life on Earth thrives at boundaries, where rivers meet the sea, where hot springs bubble up through cold ocean floors, where sunlight penetrates into the depths. The edge of an eyeball ocean would be one vast boundary, a ring of transition zones where different conditions meet and mingle. The circulation of such an ocean would be unlike anything on Earth. Heat would radiate outward from the center, driving currents toward the frozen edges. Cold water would sink and flow back toward the substellar point along the ocean floor. This constant cycling would distribute nutrients, mixing the waters in patterns we're only beginning to model with our computers. Above this alien sea, the atmosphere would be in constant motion. Water evaporating from the warm center would rise and flow toward the night side, where it would freeze and fall. But some of it might circle back, carried by winds that blow from the cold side to the warm side at lower altitudes. The planet might develop a massive atmospheric circulation cell, a global conveyor belt of air and moisture driven by the eternal temperature difference between day and night. This atmospheric transport is crucial. Without it, all the water might eventually migrate to the night side and freeze permanently, leaving the day side as dry as a desert. The planet would lose its eye. But if the atmosphere is thick enough, if the winds are strong enough, water can keep cycling, maintaining that precious ocean against the constant pull of the cold. The Terminator, that ring where day meets night, would be a region of perpetual twilight. The star would hang forever on the horizon, never rising, never setting. Shadows would stretch infinitely long across a landscape of ice and rock. The light would be red and dim, filtered through the maximum amount of atmosphere, creating an eternal sunset that never ends. This Terminator region might be the most interesting place on the entire planet. The temperatures here would be moderate, caught between the extremes of eternal day and eternal night. If there is land along the Terminator, it might be the most habitable zone on the world. Streams might flow from the glaciers, carving channels toward the warm side. The air might be breathable here, neither scorching nor frozen. Some scientists have proposed that life might find its best foothold in this twilight ring. Photosynthetic organisms could capture the dim light of the eternal horizon. They would not need to adapt to daily cycles of light and dark, to the changing angles of a moving sun. Instead, they could optimize for one specific level of illumination, one specific direction of light forever. But the cold eyeball is only one possibility. Move the planet a little closer to its star, and everything changes. On a hot eyeball planet, the substellar point receives too much energy. Water cannot remain liquid there. It boils away, perhaps escaping into space over millions of years, or perhaps condensing elsewhere on the planet. The center of the dayside might be a blasted wasteland of bare rock, scorched by radiation, too hot for any known form of life. The ocean, if one exists, would be pushed outward, forming a ring around the hottest zone rather than a circle at its center. Picture a donut of water surrounding a desert, itself surrounded by ice. The habitable zone becomes an annulus, a ring within a ring, caught between too much heat and too much cold. This ring ocean might be quite narrow, depending on the planet's conditions. The inner edge would be where water boils. The outer edge would be where water freezes. Between them, a band of liquid, perhaps only hundreds of kilometers wide, encircling the planet's dayside like a moat around a forbidden castle. The hot eyeball presents different challenges for any potential life. The innermost regions would be bombarded with radiation. The outer regions would be starved for energy. But that ring of ocean would receive a Goldilocks amount of stellar energy, not too much, not too little. And the circulation within such a ring would be complex, driven by temperature differences in multiple directions. Some hot eyeball planets might not have any surface water at all. If the planet is close enough to its star, the dayside might be hot enough to melt rock. Lava could flow across the substellar point, creating a magma ocean that glows with its own light. The night side might still be frozen, but now the contrast is even more extreme. One side burns with molten stone. The other side freezes under eternal stars. The eye becomes a portal to hell. These lava eyeball planets are probably not good candidates for life as we know it, but they tell us something important about the diversity of worlds in our galaxy. The universe is not limited to Earth-like planets with Earth-like conditions. It experiments endlessly, creating combinations we never would have predicted. And here is something remarkable. We have actually found planets that might be eyeballs. The TRAPPIST-1 system, just 40 light years away, contains 7 Earth-sized planets orbiting a dim red dwarf star. All of them are probably tidally locked. Some of them are in the habitable zone, where liquid water could exist. When we point our telescopes at these worlds, we might be looking at eyeballs staring back at us. Proxima Centauri b, orbiting the closest star to our Sun, is another candidate. It is probably tidally locked to its small red star. If it has water, it might have an eyeball ocean. The nearest potentially habitable world to Earth might be looking at its star with a liquid gaze right now. The James Webb Space Telescope is beginning to study the atmospheres of these worlds. It looks for the chemical signatures of water vapor, carbon dioxide, methane, and other gases that might tell us about conditions on the surface. In the coming years, we might learn whether these planets have atmospheres at all, and if so, what those atmospheres contain. Detecting an eyeball ocean directly is beyond our current capabilities. We cannot see the surfaces of exoplanets as anything more than points of light, but we can infer things from the light that reaches us. A planet with a large dayside ocean might reflect light differently than a planet with a dry dayside. As our instruments improve, we might be able to distinguish between different types of eyeballs. The search for life on these worlds will require new ways of thinking. On Earth, we look for biosignatures, chemical signs that life is present. Oxygen in the atmosphere, for example, is produced by photosynthesis. Methane can be produced by living organisms. But on an eyeball planet, the atmospheric chemistry would be different. The circulation patterns would concentrate certain gases in certain regions. We will need to build new models, run new simulations, develop new intuitions about what life would look like on a world so different from our own. Some researchers have proposed that eyeball planets might actually be more common sites for life than Earth-like planets. The reasoning is simple. Red dwarf stars are by far the most common type of star in the galaxy. They make up about 70% of all stars. They live for trillions of years, far longer than stars like our Sun, giving life more time to evolve. And the planets in their habitable zones are almost certainly tidally locked. If life can arise on eyeball planets, then life might be everywhere. The galaxy might be full of creatures that have never seen a sunrise, never experienced a season, never known a sky that changes from day to night. Their concept of time will be different from ours. They would measure existence not by the rhythm of rotating days, but by other cycles, perhaps the migration of weather patterns, or the slow drift of continents, or the pulsing of their stars' occasional flares. Speaking of flares, This is one of the great challenges facing life on eyeball planets. Red dwarf stars are often active, emitting powerful flares that would bathe nearby planets in deadly radiation. An eyeball planet has no rotation to help it recover from such events. The same side always faces the star, always receives the flares. Life would need protection. A thick atmosphere could provide some shielding. So could an ocean. Water is excellent at absorbing radiation, and life beneath the surface of an eyeball ocean might be protected from even the worst stellar tantrums. This is another argument for the habitability of these strange worlds. The very feature that makes them weird, the permanent dayside, also provides a permanent refuge under the waves. But atmosphere presents its own puzzles on an eyeball planet. The extreme temperature difference between day and night should drive fierce winds. Some models predict winds of hundreds of kilometers per hour, roaring eternally from the cold side to the hot side and back again at different altitudes. These winds would redistribute heat, moderating the temperature extremes, but they might also make the surface inhospitable to anything that cannot anchor itself against the gale. The interplay between atmosphere and ocean would create complex weather. Storms might form at the terminator, where warm, moist air meets cold, dry air. Rain might fall along the edge of the eyeball ocean, constantly at the boundary between liquid and frozen. Lightning might flicker in the permanent twilight, illuminating landscapes we can barely imagine. Let us think more carefully about what it would be like to stand on such a world. You land your spacecraft on the night side, where it is safe from the stellar radiation. The ground beneath you is ice, ancient ice that has not seen light in billions of years. Above you, stars will slowly across the sky, their motion a reflection of your planet's slow orbit around its star, not any rotation of the world itself. The star you orbit is not visible. It lies beyond the curved horizon, illuminating the other half of your world. You begin walking toward the terminator. The ice gives way to rock as you climb toward regions that receive some indirect light. The temperature rises slowly. After hundreds of kilometers, you begin to see a glow on the horizon. Not a sunrise, because the sun will never fully rise. Just a brightening, a reddening, as you approach the twilight zone. At the terminator, you stand in eternal dusk. The star hangs on the horizon like a bloated red ember, 50 times larger in the sky than our sun appears from Earth, because you are so close to it. Its light is red and gentle, casting long shadows behind every boulder and ridge. The sky above you is dark enough to see stars, but the horizon glows with color. Streamers of cloud rush overhead, part of the global circulation carrying moisture from day to night. If there's an ocean, it lies ahead of you toward the star. You continue walking, and the star climbs slightly higher. The temperature continues to rise. Eventually, you see it, the edge of the sea. Water laps against shores of ice and rock. The surface steams slightly in the warmer air. This is the boundary you have traveled so far to find. The pupil of the planetary eye. You could wade into this water in a suitable suit and swim toward the substellar point. The water would grow warmer as you went. The star would climb higher in the sky. At some point, you might need to dive beneath the surface to escape the heat and radiation. Down there, in the depths, the temperature would be more stable. You might find hydrothermal vents places where the planet's internal heat seeps out, creating oases of warmth and chemistry. What would live in such an ocean? We can only speculate. On Earth, the deep ocean hosts life forms that are almost unimaginably strange. Creatures that live without sunlight, deriving energy from chemical reactions at volcanic vents. An eyeball ocean might have something similar, but the geometry would be different. Light would be available from above, at least in the shallower regions. Photosynthesis might be possible across the entire surface of the ocean, not just near the edges. The productivity of such an ocean might be enormous. On Earth, photosynthesis is limited by the amount of sunlight reaching the water, which varies with latitude, season, and time of day. On an eyeball planet, the central ocean receives constant illumination at its maximum level. There is no night to interrupt photosynthesis. There are no polar regions receiving only glancing light. The entire ocean is optimized for energy capture, all the time, forever. This suggests that an eyeball ocean might support far more life per square kilometer than Earth's oceans do. The constant energy input could drive constant biological activity. Food webs might be more complex, more layered, more productive than anything we know. The eye might be not just alive, but teeming with life, a single vast ecosystem unlike anything in our solar system. Of course, this assumes that life arises in the first place. That is still the great unknown. We do not understand how life began on Earth, let alone whether it would begin on a world so different. The chemistry will be different. The energy sources would be distributed differently. The environmental gradients would be oriented differently. Life might find this harder, or it might find it easier. We simply do not know. What we do know is that the ingredients for life are common in the universe. Water is everywhere. Carbon compounds are everywhere. Energy sources are everywhere. The question is whether those ingredients can come together in the right way, under the right conditions, to spark the chemical reactions that lead to self-replication, evolution, and complexity. Eyeball planets offer a natural experiment in alternative habitability. They're different enough from Earth to test our assumptions, but similar enough to be recognizable. They have surfaces and atmospheres and oceans. They have temperature gradients and chemical cycles. They have all the pieces that might be needed for life, just arranged in an unusual pattern. In the coming decades, we will study these worlds in ever greater detail. New telescopes will probe their atmospheres. New missions might even send spacecraft to the nearest examples, though the journey would take decades with current technology. Each new piece of data will help us understand whether eyeball planets are sterile curiosities or vibrant homes for alien life. And even if we never find life on an eyeball planet, we will learn something profound. We will learn more about what makes a world habitable or not. We will refine our understanding of the conditions necessary for life. We will become better at predicting where to look next in our search for company in the cosmos. The cold eyeball stares at its star with an ocean of possibility. The hot eyeball glares with a ring of liquid hope. Somewhere between fire and ice, between eternal day and eternal night, life might be finding a way. And we, from our spinning world with its comforting cycle of day and night, are learning to see through alien eyes. The physics of tidal locking deserves more attention because it shapes everything about these worlds. When a planet orbits close to its star, the star's gravity raises a tidal bulge on the planet, just as our moon raises tides on Earth's oceans. But if the planet is rotating, that bulge is constantly being pulled out of alignment with the star. The star's gravity tugs on the bulge, creating a torque that slows the planet's rotation over time. Eventually, after millions or billions of years, the planet stops rotating relative to the star. One side faces starward permanently. The tidal bulge is now aligned with the star, and there is no more torque to change anything. The planet is locked. This process is inevitable for planets close to their stars. The strength of the tidal force drops off rapidly with distance, so planets farther out might take longer to lock, or might never lock during the lifetime of their star. But for planets in the habitable zones of red dwarf stars, locking is essentially guaranteed. The timescale matters. If a planet locks before life has a chance to arise, then life must adapt to eyeball conditions from the very beginning. But if a planet once rotated and then slowly locked, any existing life would face a gradual catastrophe. Imagine a world where the days grow longer and longer over millions of years. Eventually, a single day lasts for months, then years, then centuries. The final generations of rotating creatures would experience something like a permanent winter on one half of their world, a permanent summer on the other, with narrow bands of survivable climate retreating toward the terminator. Any life that survived this transition would be profoundly different from what came before. It would have evolved from rotating world ancestors into eyeball world descendants. It would carry the genetic and biochemical legacy of a different kind of existence, adapted to new conditions through millions of years of brutal natural selection. This raises fascinating questions about the evolution of life on eyeball planets. Would it be more flexible than Earth life, having survived the transition? Or would it be more rigid, optimized for eternal constancy rather than daily and seasonal change? Earth organisms are adapted to cycles. Our cells have circadian rhythms. Our bodies expect variation. Eyeball life would be adapted to stasis. Its biology would expect constancy. The psychology of such creatures, if they developed intelligence, would be almost incomprehensible to us. Think about what cycles mean for Earth life. We sleep and wake. We have seasons of growth and dormancy. We have generations that live and die in rhythms tied to planetary motion. Our cultures mark time by the movement of sun and stars. Our religions celebrate solstices and equinoxes. Our agriculture follows the cycle of seasons. Everything about human existence is built on the assumption that day follows night follows day, that winter follows summer follows winter. On an eyeball planet, none of this applies. There would be no time cues from the sky, no daily rhythm to entrain biological clocks, no seasonal variation to drive cycles of reproduction and dormancy. Time would have to be measured by other means, perhaps by internal clocks, or by the slow precession of stars across the night-side sky, or by geological processes, or by purely artificial measures. An intelligent species on such a world might have a completely different relationship with time. They might not have concepts like morning and evening, spring and autumn. They might think of existence as fundamentally static, with change being exceptional rather than normal. Their philosophy might emphasize permanence rather than flux. Their mathematics might focus on steady states rather than dynamics. Or perhaps they would be obsessed with change precisely because it is so rare. Perhaps any variation in their constant world would be noticed and celebrated. A shift in the stellar wind, a volcanic eruption, a change in the weather patterns. These might be the events that structure their history, the punctuation marks in an otherwise unchanging sentence. Their geography would certainly be different. On Earth, we navigate by the sun. East is where the sun rises. West is where it sets. We orient our maps with north at the top by convention, but we use the sun to find our way. On an eyeball planet, the star does not move. It hangs in a fixed position in the sky, higher if you're closer to the substellar point, lower if you're near the terminator. Navigation would be simple in some ways. You would always know which way starward is. But the concepts of east and west would not exist as we understand them. Perhaps they would navigate by temperature gradient, warm ward and cold ward, or by light level, bright ward and dark ward. Their maps might be centered on the substellar point, with concentric rings showing zones of decreasing temperature and light. The terminator would be a prominent feature on any map, a ring dividing the known world from the frozen unknown. Would they explore the night side? That would depend on their technology and their curiosity. The night side is brutally cold, completely dark except for starlight, and apparently devoid of liquid water or other resources. It might be seen as a wasteland, a void, a realm of death. Or it might be seen as a mystery, a challenge, a frontier to be conquered. The first expeditions to the night side would be daunting. You would leave the light behind, watching the stars sink toward the horizon and then below it. The temperature would drop rapidly. You would enter a world lit only by stars, colder than anything on the dayside, hostile to life in every way. What would you hope to find there? Ancient ice preserving records of the planet's early history. Minerals deposited by some long ago geological process. Perhaps even evidence that the planet once rotated, fossils of creatures that lived before the Great Locking. The ice sheets of the night side might be kilometers deep, pressing down on the rocky crust below. Might there be liquid water beneath that ice, heated by the planet's internal warmth? This is a question we ask about moons in our own solar system, like Europa and Enceladus, which have ice shells over liquid oceans heated by tidal forces. An eyeball planet might have something similar on its night side, a hidden ocean in eternal darkness, completely isolated from the illuminated ocean of the dayside. If such a night-side ocean exists, it would be a different world within a world. Its chemistry would be determined by the rocks below and the ice above, not by the star. It might have its own ecosystem, based on geothermal energy rather than stellar energy. Life that would never have seen the star would have no concept of light except perhaps as a theoretical possibility discussed by philosophers. The connection between dayside and night-side ecosystems, if both exist, would be through the atmosphere and through any subsurface water connections. Nutrients might cycle between the two halves of the planet over geological timescales. Life forms might migrate through underground channels. The planet might be more connected than it appears, a single biosphere spanning from eternal day to eternal night. This is all speculation, of course. We have no evidence that any of these possibilities are realized on any actual eyeball planet. But that is the nature of scientific exploration. We imagine possibilities, then we look for evidence, then we revise our imagination based on what we find. The more detailed our imagination, the better our questions, the more likely we are to recognize something interesting when we see it. Let us turn to the question of how we might actually detect these features on distant eyeball planets. Our current technology allows us to learn a few things about exoplanets. We can measure their size by watching how much starlight they block when they pass in front of their star. We can measure their mass by watching how much they make their star wobble gravitationally. From size and mass, we can calculate density, which tells us something about composition. More recently, we have begun to analyze the atmospheres of some exoplanets. When a planet passes in front of its star, some starlight filters through the planet's atmosphere on its way to us. Different gases absorb different wavelengths of light, leaving characteristic fingerprints in the spectrum we observe. By carefully analyzing these fingerprints, we can identify which gases are present in the atmosphere. The James Webb Space Telescope has revolutionized this field. Its unprecedented sensitivity allows it to detect atmospheric signatures that previous telescopes could not see. It has already analyzed several exoplanet atmospheres, finding water vapor, carbon dioxide, and other molecules. In the coming years, it will turn its attention to more and more potentially habitable worlds. For eyeball planets specifically, we might look for atmospheric signatures that indicate the presence of liquid water. Water vapor is an obvious target, but on an eyeball planet, water vapor might be concentrated over the dayside ocean and depleted over the frozen night side. If we can observe the planet at different phases of its orbit, we might see this asymmetry in the water vapor signal. We might also look for signs of atmospheric circulation. Models predict that eyeball planets should have distinctive wind patterns, with air rising over the warm substellar point and flowing toward the night side at high altitudes, while cold air flows back toward the substellar point at low altitudes. This circulation might leave signatures in the atmospheric chemistry, with different gases concentrated at different altitudes or in different regions. The presence of certain gases might indicate biological activity. On Earth, oxygen is maintained at high levels by photosynthesis. Without plants and cyanobacteria constantly producing it, oxygen would disappear from our atmosphere within millions of years, reacting with rocks and other materials. If we detect oxygen on an eyeball planet, along with other biosignature gases like methane, it would be strong evidence that something is producing these gases, possibly life. But we must be careful. There are non-biological processes that can also produce these gases. We need to consider the context, the planet's geology, its star's radiation, its atmospheric chemistry as a whole. A single detection does not prove life exists. We need multiple lines of evidence, a pattern that is more easily explained by biology than by geology or chemistry alone. The search for biosignatures on eyeball planets is just beginning. It will take decades of observations, increasingly sophisticated instruments, and ever more detailed models to reach any conclusions. We might find strong evidence of life within our lifetimes, or we might find that the nearest eyeball planets are barren and we need to look farther afield. Or we might find ambiguous results that leave the question open for future generations to resolve. What we will certainly find is a deeper understanding of planetary diversity. Each eyeball planet we study will teach us something about the range of conditions possible on worlds orbiting close to red dwarf stars. Even negative results are valuable. If we find that most eyeball planets lack substantial atmospheres, that tells us something about atmospheric loss processes. If we find that most have dry daysides, that tells us something about water distribution. Science advances through both successes and failures, through confirmations and surprises. There's another way we might learn about eyeball planets, one that does not require pointing telescopes at distant stars. We might learn by simulation. Increasingly powerful computers allow us to model planetary climates in ever greater detail. We can set up a virtual planet with the properties of an eyeball world, specify its size, composition, atmosphere, and distance from its star, and then let the simulation run, watching what happens to temperature, pressure, wind, precipitation, and ocean currents. These simulations have already taught us much of what we know about eyeball planets. They showed us the possibility of stable dayside oceans. They revealed the importance of atmospheric heat transport. They predicted the wind patterns and weather systems that such worlds might experience. As our computers grow more powerful and our models more sophisticated, we can explore more possibilities, test more scenarios, and develop better intuitions about these alien environments. Some researchers are even beginning to simulate the potential evolution of life on eyeball planets. These are highly speculative exercises, building on our limited understanding of how life arises and evolves. But they push us to think carefully about what constraints an eyeball environment would place on living things. Would photosynthesis evolve differently? Would multicellular life face different challenges? Would intelligence develop along different paths? These are questions we cannot answer definitively, but thinking about them sharpens our understanding of both life and planets. The study of eyeball planets is part of a broader revolution in our understanding of the universe. For most of human history, we knew of only one planetary system, our own. We knew of only one planet with liquid water, our own. We knew of only one world with life, our own. Our imagination was constrained by our limited sample size. Now we know of thousands of planets orbiting other stars. We have found worlds larger than Jupiter orbiting closer to their stars than Mercury orbits ours. We have found small rocky worlds in the habitable zones of red dwarf stars. We have found planets orbiting two stars at once, planets with densities suggesting they're made of water, planets so hot that their atmospheres contain vaporized rock. The diversity is staggering. In this context, eyeball planets are not strange. They are normal, at least for a certain class of star. Our spinning, tempered Earth is the oddity, a planet that happened to form far enough from its star to avoid tidal locking, around a star stable enough not to bombard it with lethal flares, with a moon large enough to stabilize its axial tilt. We're the unusual ones. The eyeballs are the norm. This realization has profound implications for the search for life. If eyeball planets are common and can be habitable, then the number of potential homes for life in the galaxy increases dramatically. Red dwarf stars are everywhere, and they live for a very long time. Each one might host multiple, potentially habitable eyeball planets. The galaxy might be full of life, just not the kind of life that looks up at a sun that rises and sets. Of course, commonality does not guarantee habitability. Just because a planet could support life does not mean it does. The conditions might be right, but life might never get started. Or it might get started and then be wiped out by some catastrophe. Or it might be so different from Earth life that we fail to recognize it as life at all. The search for life is also a search for humility, a reminder that our assumptions might be wrong and our categories might be too narrow. The astronomers and biologists working on this problem are acutely aware of these challenges. They are developing new frameworks for thinking about habitability, new definitions of what counts as a biosignature, new methods for detecting the subtle signs of life on distant worlds. It is painstaking work, often frustrating, but occasionally thrilling when a new discovery opens up new possibilities. Among the most exciting recent developments is the realization that the atmospheres of some potentially habitable planets are within reach of current technology. We do not have to wait for future telescopes. We can start now with the James Webb Space Telescope and ground-based observatories to probe the air of worlds that might be eyeballs. Each observation is a glimpse into an alien environment, a data point in the growing catalog of planetary diversity. The TRAPPIST. One system remains a prime target. 7 Earth-sized planets, all probably tidally locked, 3 or 4 in the habitable zone. One of them, TRAPPIST 1e, is considered particularly promising. It receives about the same amount of energy from its star as Earth receives from the Sun. If it has an atmosphere and water, it might have a substantial eyeball ocean. It is 40 light years away, close enough that its light reaches us in less than half a human lifetime. Far enough that visiting it is beyond any technology we can currently envision. Observations of TRAPPIST-1 planets have already yielded intriguing results. Some of the inner planets appear to have lost any atmospheres they might have had, stripped away by their star's radiation. The outer planets, including TRAPPIST-1e, are more likely to have retained their air. Upcoming observations will tell us more about what that air contains. Proxima Centauri b, the nearest known potentially habitable exoplanet, presents different challenges. It is closer, only 4 light years away, but its star is active and prone to powerful flares. Any life on Proxima b would need to survive these periodic irradiations. An ocean would help, absorbing the radiation and shielding anything living beneath the waves. But the flares might also strip away the atmosphere over time, leaving a barren rock exposed to the vacuum of space. The European Extremely Large Telescope, under construction in Chile, will have the resolution to observe these nearby planets in more detail than ever before. It might even be able to directly image some of them, separating the planet's light from the star's light and analyzing it separately. This would allow us to study the composition and conditions on these worlds with unprecedented precision. Beyond observation, there is the tantalizing possibility of exploration. Spacecraft travel slowly compared to light, but they can carry instruments that telescopes cannot. A probe sent to Proxima Centauri b would take tens of thousands of years with current technology. But new propulsion concepts, like light sails pushed by powerful lasers, might reduce the travel time to decades. The Breakthrough Starshot Initiative is studying this possibility, aiming to send a tiny probe to Proxima Centauri within a generation. Such a probe would not orbit the planet or land on it. It would fly by at a substantial fraction of the speed of light, taking pictures and measurements for a few precious hours as it passed. But even a brief encounter would tell us more than centuries of telescope observations. We might see the eyeball directly, the ocean glinting in the red light of its star, the ice sheets spreading across the night side. We might detect signs of life or confirm that the planet is a sterile rock. Either answer would be historic. The idea of interstellar exploration seems like science fiction, but science fiction has a way of becoming science fact. 100 years ago, no one had left Earth's surface. 50 years ago, no one had walked on another world. 25 years ago, no one knew whether planets existed outside our solar system. Each generation expands the boundaries of what is possible. Our grandchildren might live in a world where probes routinely visit nearby stars. But we need not wait for interstellar travel to learn about eyeball planets. The planets in our own solar system offer analogs that can teach us about tidally locked worlds. Mercury is almost tidally locked to the Sun, rotating 3 times for every 2 orbits. It experiences extreme temperature differences between its day and night sides, though not as extreme as a truly locked planet would. Venus rotates so slowly that its day is longer than its year, creating something like a quasi-locked situation. More intriguingly, many of the moons of our outer planets are tidally locked to their parent planets. Europa, orbiting Jupiter, keeps one face toward Jupiter at all times. It has a subsurface ocean heated by tidal flexing that might contain more liquid water than all of Earth's oceans combined. Enceladus, orbiting Saturn, also has a subsurface ocean and has been observed venting water vapor and ice into space. These moons are not eyeball planets, since they are heated by tidal forces rather than stellar radiation, but they share some characteristics with the night-side oceans that might exist on eyeball worlds. Studying these moons teaches us about ice dynamics, subsurface oceans, and the potential for life in environments very different from Earth's surface. The lessons we learn here can inform our expectations for eyeball planets. If life can exist in the dark oceans beneath Europa's ice, it can probably exist in the dark oceans beneath an eyeball planet's night-side ice. The same chemistry, the same energy sources, the same fundamental biology. Future missions to Europa and Enceladus will probe these subsurface oceans directly. A lander might drill through kilometers of ice to reach the water below. A submarine might swim through alien seas, searching for signs of life. These missions are still being planned, but they represent the next giant leap in our exploration of potentially habitable environments. Meanwhile, here on Earth, scientists are studying extreme environments that might resemble conditions on eyeball planets. The deep ocean hydrothermal vents, where life thrives without sunlight. The ice-covered lakes of Antarctica, where microbes survive in cold and darkness. The hot springs, where organisms live at temperatures that would kill most life. Each of these environments teaches us something about the limits of life, the conditions under which it can persist, and the adaptations it develops. Astrobiology the study of life in the universe, is fundamentally a search for principles. What are the essential requirements for life? What conditions are compatible with it? And what conditions preclude it? What signatures would life leave that we could detect from afar? These are questions that span astronomy, biology, chemistry, geology, and philosophy. They are among the deepest questions humans have ever asked. Eyeball planets force us to confront these questions in new ways. They strip away the familiar features of Earth, the day-night cycle, the seasons, the global distribution of temperatures, and ask us to imagine life without them. In doing so, they reveal which of our assumptions about life are truly fundamental and which are mere accidents of our particular planetary home. Consider the concept of circadian rhythms. Almost all life on Earth has internal clocks that operate on roughly 24-hour cycles, synced to the planet's rotation. These clocks regulate sleep, metabolism, behavior, and countless other processes. They are so pervasive that we tend to assume they are essential. But on an eyeball planet, there is no 24-hour cycle. Would life there have circadian rhythms? Would it need them? Or would it develop entirely different ways of organizing its internal processes? The answer might depend on whether any rhythms exist in the eyeball environment. Perhaps the star emits periodic flares that create a rough cycle. Perhaps geological processes create regular disturbances. Perhaps the organisms themselves create rhythms through their collective behavior, like the way fireflies synchronize their flashing. Or perhaps life on an eyeball planet simply does without rhythms, existing in a state of constant activity or constant rest. This kind of thinking is valuable even if we never find life on an eyeball planet. It forces us to examine our assumptions, to distinguish between what is universal and what is particular, to prepare our minds for the unexpected. The universe is under no obligation to match our expectations. The more flexible our thinking, the better we will understand whatever we discover. Let us return to the physical structure of eyeball planets and consider some variations we have not yet explored. So far, we have discussed planets with substantial atmospheres and oceans. But what about eyeball planets with thin atmospheres, or none at all? A planet without an atmosphere would be even more extreme than one with. There would be no winds to transport heat from day to night. The temperature difference between the two hemispheres will be maximized. The dayside might be hot enough to glow with thermal radiation, while the night side might be colder than any place in our solar system, approaching absolute zero. On such a world, any water would be confined to a narrow ring at the terminator, where temperatures might be just right for liquid. This ring might be only a few kilometers wide, a thin band of habitability on an otherwise hostile world. Life there would be precarious, confined to a narrow strip, vulnerable to any perturbation that shifted the temperature balance. Or consider a planet with a very thick atmosphere. Such a planet might have more moderate temperature differences, as the atmosphere would efficiently transport heat. The ocean might extend beyond the substellar point, covering more of the dayside. The terminator might be a gradual transition rather than a sharp boundary. The planet might look less like an eye and more like a world with strange geography, a single large continent of ice surrounding a single large ocean. The composition of the atmosphere also matters. An atmosphere rich in greenhouse gases would trap heat, raising temperatures across the planet. An atmosphere with reflective clouds might cool the dayside by reflecting stellar radiation back to space. An atmosphere with absorbing hazes might heat up at high altitudes, creating temperature inversions. Each variation creates a different climate, a different set of conditions for potential life. The planet's geology matters too. A planet with active plate tectonics might have volcanoes that pump gases into the atmosphere, maintaining conditions suitable for liquid water. A planet without tectonics might lose its atmosphere over time, drifting toward the extreme case of a bare rock with a terminator ring of water. The size of the planet, its composition, its internal heat, and its geological activity all influence its long-term evolution and habitability. The history of the planet matters as well. How did it form? How much water did it start with? Has it always been in its current orbit, or did it migrate from elsewhere in its solar system? Did it ever have a moon, and if so, what happened to it? Each of these factors shapes the planet's present state and its prospects for hosting life. We should also consider the possibility that some eyeball planets might not be planets at all, but moons. A large moon orbiting a gas giant in the habitable zone of a red dwarf star would likely be tidally locked to the star, not to its parent planet, if the star is close enough. Such a moon could have eyeball characteristics while also experiencing additional heating from tidal flexing, like Europa and Enceladus in our own solar system. A gas giant in the habitable zone might host multiple such moons, creating a system of eyeball worlds orbiting a common center. The moons would see each other in their skies, passing in front of the star, casting shadows on each other. The gravitational interactions might create complex dynamics, with each moon's orbit being perturbed by the others. This would be a very different environment from a lone eyeball planet, with opportunities for exchange between worlds and additional sources of energy from tidal heating. The possibilities multiply the more we think about them. The universe is creative, far more creative than we are. Every variation we imagine, it has probably realized somewhere. And many variations we have not imagined, it has realized too. Our job is to open our minds wide enough to encompass the diversity that exists, to let go of our Earth-centric assumptions, and to look for what is actually there rather than what we expect to find. This openness is the essence of science. We do not discover truth by insisting that the universe conform to our preconceptions. We discover truth by observing carefully, thinking clearly, and revising our beliefs when the evidence demands it. The study of eyeball planets is an exercise in this kind of intellectual humility. So where do we stand? We know that eyeball planets exist. We have found them orbiting nearby stars. We understand the physics that creates them and the conditions they are likely to experience. We have modeled their climates and speculated about their potential for life. We are beginning to observe them with powerful telescopes, searching for atmospheric signatures that might tell us more about their surfaces. We do not yet know whether any eyeball planet hosts life. We do not know whether their oceans actually exist or whether they are theoretical possibilities that nature has not realized. We do not know whether the conditions at their terminators are hospitable or hostile. We do not know whether their atmospheres protect them from stellar radiation or leave them exposed. These are questions we will answer in the coming decades. The tools are being built. The observations are being planned. The scientists are working. Each year brings new discoveries, new constraints, new surprises. The story of eyeball planets is just beginning. And perhaps, somewhere out there, that story includes life. Perhaps an ocean stares up at a red star, and somewhere in that ocean, something stirs. Something that has never seen darkness. Something that has never experienced a sunrise. Something utterly alien, yet fundamentally familiar, made of the same atoms, following the same chemical principles, striving toward complexity and persistence in its own strange way. If that life exists, it does not know we're looking for it. It does not know that across 40 light years of space, another form of life gazes up at the stars and wonders. It simply lives in whatever way it lives, adapted to its eternal day and eternal night, at home in a universe far stranger than either of us can fully comprehend. That is the promise and the challenge of the search for life beyond Earth. We reach out across distances almost too vast to imagine, searching for something we might not recognize when we find it. We build telescopes and spacecraft. We develop theories and models. We argue and observe and speculate, all in the hope of answering the oldest question: are we alone? The eyeball planets offer one possible answer. They are different from Earth, but not impossibly so. They are strange, but not unknowable. They challenge our assumptions, but do not shatter our frameworks. If life can exist on an eyeball planet, then life might be a common phenomenon in the universe, arising wherever conditions permit. If life cannot exist on these worlds, despite their liquid water and stable environments, then we need to understand why, and that understanding will deepen our knowledge of life itself. Either way, we learn. Either way, we grow. Either way, we move closer to the truth about our place in the cosmos. The eyeball planets stare at their stars, and we stare back at them, two forms of existence connected by light across the void. What we discover about them, we discover about ourselves. What questions they pose, we must find the courage to answer. The night sky is full of red dwarf stars, tiny and dim, easy to overlook. Each one might host planets. Each planet might be an eyeball. Each eyeball might harbor an ocean. Each ocean might teem with life. The numbers are vast, the possibilities endless. And we are only beginning to look. This is the golden age of exoplanet science. We are the first generation to know for certain that planets exist beyond our solar system. We are the first to see them, measure them, analyze them. We're the first to seriously search for life among them. Whatever we find, we will be remembered for this search. Future generations will look back at us as the pioneers who opened the door to a universe of worlds. The eyeball planets await our scrutiny. Cold and hot, wet and dry, lifeless and perhaps living, they orbit their ancient stars in patient silence. They have waited billions of years for us to notice them. They can wait a little longer while we build better tools and develop sharper questions. But we should not wait too long. The universe does not owe us answers. If we want to know what lies beyond our small blue world, we must make the effort to find out. We must fund the telescopes, train the scientists, launch the spacecraft, and do the hard work of discovery. The eyeball planets will not come to us. We must go to them with our instruments and our imaginations, ready to be surprised. The eye stares at its star. We stare at the eye. Somewhere between us, the truth waits to be found. Let's not rest until we find it.